So now that we kind of got our feet wet about using the structural elements in a very simple manner, it's a good way to start because we got to see how they're created. We got to see how we can put a liner on the face of zones, which is ideal for creating liners. And then we got to run and look at some of the response. So now we'll talk a little bit about the mechanics. And this is going to be like the briefest mechanics introduction that you'll ever have in your life, probably, because all of this in great detail is in the documentation. And I highly encourage you, if you really want to, you can look at it there. But this is going to be super, super plain, easy and quick. All right. The main idea is that all these elements in FLAC2D are one element, one beam element, the line, and then two nodes. And the way that all this is ran is that we sum internal forces at each node to get a resultant force. So that's kind of what I'm showing here. We have these R forces. This is a explicit scheme, in which case there is a time step we take to determine the new velocities from the forces and mass and other properties of these elements. We can compute displacement at each increment, which is simply just the velocity, which is calculated in the scheme times the time step. And remember, like, these time steps are exactly the same as the time step in that you talked about in yesterday when Andre introduced it for the zones. So your zones will have a time step that's based on the zone's Young's modulus and the size. Structural elements are the same. They will have a time step based on their properties, such as Young's modulus and the size of the element. Generally, not always, but generally, the time step will always be the smaller of the two, right? Because if you're taking too large of a time step for structural elements, you could generate instabilities. And usually, when using structural elements, you're using an element that supports soil, which is much softer. So you might have like soil nails made of steel. You might have cables made of steel. Very stiff, very small. So these time steps for structural elements might dominate your whole runtime. It's just something to keep in mind. Okay, then we update internal forces based on the displacements and the stiffness matrix. And finite element courses that you may or may not have taken, stiffness matrices are the first thing you learn about. It's basically a matrix for each type. Actually, I'll go to the next slide. What is a stiffness matrix? It is this. It's basically a matrix that's built up upon its geometry and moment of inertia. It will be different for different types of structural elements. It will have different degrees of freedoms for different codes. In FLAC3D, this is a 12 by 12 matrix. In FLAC2D, this is a 6 by 6 matrix. And it basically just depends on how many degrees of freedom. So for us, always 3 degrees of freedom for each node. 2 translational, XY, only rotates in one direction. That direction is out of plane. So that basically gives us a total for the element of 6 degrees of freedom, and that's why this is a 6 by 6 matrix. Oh, did it go the wrong way? I think it did. Okay. Yeah, then this is just the same slide. Okay, I'm not going to go into that then. All right, so that was like the easiest, the quickest finite element explanation you can possibly give. The entire explanation is in the documentation, and I'm going to actually go to it. Oops. I wonder if you can click on it in the, yeah, yay. It is here, called General Formulation of Structural Element Logic. And it's basically kind of at the bottom of the world we live in here. And in it, it talks about all this good stuff. Links, finite elements, which I gave you a very brief discussion of. You can see I'm not going into stress recovery, governing equations, blah, 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 mass matrix. I will briefly mention damping, and we'll leave it at that, just because that talking about all this would be a whole nother day. But if you want to look into it, I highly encourage you to read this part of the documentation. All right, cool. So a brief note on damping. Damping must be specified, just like we will specify damping for your zones. There's damping for structural elements. Two options: local default, it damps high frequency motion to keep the model in a quasi-static state. Combine local, like local damping, but handles cases of imposed uniform motion. Combined local damping is generally done when you're initializing your model, say under gravity. It's all moving down. Gravity force vector is moving it down. It will basically just converge faster. You could use local damping. That's totally fine. Rayleigh damping is specific to only dynamics. Dynamics is a whole nother animal within FLAC2D. And if you're using dynamics, earthquakes, that kind of thing, and you use structural elements, you will need to use Rayleigh damping, or soon in the future, Maxwell damping will be included. Two types of damping that are specific to dynamic damping, really good at taking out quick spurious motion. Okay. And then this slide is just kind of showing that even if you use local damping or combined damping, the same final static equilibrium state is the same. So this is just a beam given uniform pressure, just applied with using the two different damping schemes, but the final state's the same. And that's important. All right. Uniformly loaded beam. We're going to skip that for now because of time. And we're going to get through the rest of these slides and then go into more of a practical example where we do the pile end bearing test. All right, so I'm going to jump a little bit more into coupling. Remember, coupling, I mean by linking or zone grid interaction. And I've hit on this quite a bit already, but we'll just reiterate some more here. So coupling, there's two different types. So right here we have node to zone. You can also couple nodes, and when I say nodes, just keep in mind a node is with a structural element. A grid point is with a zone. So I'll try to keep that distinguished. So you can couple nodes to other nodes. What I'm saying there is you can couple like a pile to basically maybe concrete sheet on top. That's a very typical civil application where they have piles and then some sort of concrete bed on top that's connected to the piles. I forget the exact name in civil engineering what it's called, but done a lot. And they need a way to connect the pile to the concrete sheet, and you can specify how that interaction will take place. It can be rigid. A lot of times that's bad because high stresses will develop that rigid contact or connection, I should say. Or you can define it to be deformable and give it your own stiffness and other properties. But for now, we're going to just focus on how the nodes connect to the zone or how they connect to the grid. So this is a very simple example. You have a cable going through a grid. Like Ed said over there, it doesn't matter where the cable is, just as long as it's inside the grid. So what FLAC2D will do, it'll take your target position of that node, and you would think, oh, this is pretty easy to find the zone. It's just find one zone that it encompasses. The problem that gets harder is maybe you have like 10 nodes within this one zone. Do they all connect to it? Probably. It's a bad way to model, but that has to be sorted out. Okay, so like I did mention this, that the nodes each have their local coordinate system. This will be automatically calculated for you. One thing to note is that when you create the structural element, the local coordinate system will be the same as the global system. It's not until you start cycling will it adjust to create the local coordinate system along the actual axis of the element. it's kind of, you don't really need to worry about that. Just know that most of these local coordinate systems will be done automatically for you. It's only when you're getting into like some very complicated geometry you have to start thinking about that a bit more. Okay. Let's see, what is this thing? Connects node to a target. In this case, the target is a zone or node. Node local coordinate system is then defined, and each degree of freedom has an attachment condition. What I mean by that is basically how does the node interact with the grid? For these types, beams, piles, liners, what have you, all these attachment conditions are predefined. You'll remember all those coupling keywords like coupling stiffness normal, coupling stiffness shear. That's all predefined for you. You just need to fill in the values. You can yourself, and we won't go into detail, you can make your own interaction. You can define it as free, rigid, or deformable. If you define it as deformable, then you'll have to specify things like stiffness, both in the normal and shear direction. But just know that the only three attachment conditions possible are whether it's being free, rigid, or deformable. Not that important, because whenever you say create me a beam, create me a pile, all these attachment conditions are predefined and you just have to put in the properties. Okay, beams, a little more in depth. Let's just bring this all out. This is kind of an ugly slide, I apologize. Simple element, the most simple element. One element, two nodes. They can translate in the X and Y direction, and they can rotate out of plane. Simple as that. So forces, X and Y forces, and moments. One thing that we added, and it's not so necessary, but it became necessary for some of the consultants' work, was that most of the times the beams we're dealing with are long and slender. And in beam theory, this is specifically called an Euler-Bernoulli beam. Because of its geometry, a long thin plate or beam, forget I said plate, that's for 3D. The neutral, or if you were to draw a line right down the center of that beam, start bending it, that line will stay linear. And that is just a effect of long thin beams, or commonly called Euler-Bernoulli beams. If that becomes a short, thick beam, and say you have basically like a block like this, you could start bending it, ideally, and that line that you drew would actually start to curve. And these are typically called Timoshenko beams. 90% of the time, you would be using an Euler-Bernoulli beam. That is the default. And that basically all you do is assign a Young's and Poisson's modulus. If for some reason you're modeling a short, thick beam, I don't know which scenario, honestly, you'll be required to add a couple more properties. Like I said, most of the time it will be long Euler-Bernoulli. Okay, and then I kind of showed this already. So beam properties, they're all listed in the documentation. It's kind of the documentation was decided to be a FLAC2D documentation, and there are snippets in there that says, oh, this is 2D only. And the motivation was that we didn't want to write a whole new documentation set, honestly. So a lot of the number of properties here is how many are actually in 3D. And you can go through it and, like as I pointed out, find the ones that are 2D only. Those are the properties. For example, moment of inertia. If your beam is of square shape, you can easily calculate the moment of inertia to be based on the height cubed divided by 12. If it's a circle, then you'll be calculating a different moment of inertia. Okay, piles, remember, are just the element behaves just like a beam. The only difference now is how it interacts with the grid. So shear coupling for a pile, shear behavior is cohesive and frictional, like a cable. So what I'm showing here is basically just the shear strength criterion. The quantities you supply for the shear direction for coupling is stiffness, Ks, shear, cohesion in the shear direction, and then friction in the shear direction. Similarly, in the normal direction, the coupling is exactly the same. You can give a normal stiffness, cohesion in the normal direction, and friction in the normal direction. It might seem kind of counterintuitive that you're providing cohesion and friction in the normal direction when most of the time you'll be putting in cohesion and friction in a shear direction. But there are cases where you will provide friction in the normal direction. Usually you're just providing a stiffness and a cohesion. And then that would equate to like perhaps your pile that you just slammed into the ground is cemented in place. Just coming up with things off the top of my head. So now there's going to be some strength in the normal direction. Okay, so pile properties, the way these are listed is there's always going to be a disclaimer before that says, oh, the first 10 properties are the same as the beam because a pile is really just a beam element with the addition of special coupling spring properties, which are all listed here. And I think now we'll talk, oh yes, and then rock bolts. Rock bolts are a special type of pile that allows strain softening and tensile yielding of the actual bolt itself. Okay, and then one thing I wanted to highlight was stiffnesses. So stiffnesses for these coupling springs are not something you can just look up in any handbook and be like, oh, the stiffness between I know 440 steel and dolomite is this and this. That doesn't exist. So the idea is to set stiffnesses to minimize pile zone overlap. What does that mean? So you could say, well, I'm not going to worry about the stiffness. I don't care. Let's make it extremely small. And if you do that, you're basically saying that this whole element, all the nodes in it can just move through the entire grid with very little resistance. So it's great that you have a small stiffness because that, higher stiffness affects the time step, but it's not going to be anything close to reality. What is generally done is that the stiffnesses are set according to zone properties. And that's listed right here. So it's common to select the stiffnesses to be 10 times this equation, which is, this is the bulk modulus and this is the shear modulus of the zone. And it depends on the zone size, where Z min is the smallest dimension of any adjoining zone in the normal direction. Now that can be hard to find because your structural element might be going through zones that are of different size. I mean, when you create an unstructured mesh, these sizes are different. So generally, you just find the smallest zone that's your structural element is linked to, and you use that in this equation. What almost always happens, and is completely fine, is that you have a Young's modulus of 100, for example, for your material, for your zones. What people always do is they just increase that by a factor of 10 for the stiffness of their structural elements. So the stiffness will be, both in normal and shear direction, 1,000. Will it drastically change the results if you put in a different stiffness? It will if it's less than 100. So if you put in a stiffness of 1, that will be wrong. If you put in a stiffness of 1,000,000, that'll be great, but you will be cycling forever. And because the higher the stiffness, which affects the time step, the smaller the time step will be, and the longer it will take to run your model. So just note that pretty much in all applications I've seen, people have just multiplied the stiffness by 10 from what the zone's Young's modulus is. If you want to be very thorough, you can go through each one and use this equation and change it. Okay, so that was it for piles. And now we move our attention to liners. So really liners are very similar to piles. The only difference is that they are plane strain elements, which means they are continuous out of plane. The other noticeable difference is if you would look at this shear strength criterion, they actually have a residual cohesive value. So there are like these subtle differences between how the grid interacts. These subtle differences are meant to actually mimic the actual object. Liners are, concrete liners or shotcrete, something like that. That's what these subtle differences are really trying to reflect those, what kind of object it is. Normal coupling for liners is different. It basically has just a stiffness and a tensile strength. So you can imagine that spray-on shotcrete, that interaction between the concrete and the rock for liners basically can deform to a value, pulling apart, and then it ruptures. Simple as that. Okay, so here are all the properties for liners. There's the link to them. You can check it out. There's a lot. Okay, and then this slide is just simply kind of to reiterate that liner elements represent a structure that is continuous in the direction perpendicular to the analysis plane. That is called a plane strain condition. So you might ask yourself, well, plane strain is the entire modeling scheme for FLAC2D. It's actually 2.5D. It basically means that you can actually get the out of plane stresses. That is not the case for structural elements. For structural elements, they are all plane stress elements. That means that the stress out of plane is always zero. And that's basically the end of story. That's how it is. We have ideas of introducing plane strain elements into the code, but an easy way of creating a plane strain element is just by dividing 1 minus nu squared. And that is always automatically done for liners. If say you like the pile element and you want to make a pile continuous out of plane, all you would do is take your Young's modulus and divide it by 1 minus nu squared. And now you have a continuous out of plane element. Keep in mind though that you cannot retrieve the out of plane stresses, which you can do in FLAC2D for the zones. All right, lastly, we have cables. And yeah, there's not much to say about cable except for that they are probably the simplest element in that they only move in one direction. So each node has 1 degree of freedom, and that's along the axis of the cable. So these things are entirely shear dependent. So there's no normal forces. And it's a little confusing. We kind of dropped the idea of coupling in the normal shear direction, and because it's only in the shear direction, we just call it grout. So the grout has its own properties, stiffness, cohesion, and friction. Do all the cables have to be grouted? No, you wouldn't assign those grout properties, and then you would just have a dry cable inside a rock mass. All right, so here's all the cable properties. Since cables are so fundamentally different than beams, we just list all the cable properties and we don't list like, oh, see the other 10 beam properties. So yeah. Oh yes, there is a little bit of documentation on how to estimate these grout properties. Again, just like estimating the stiffness, or the coupling stiffness. There are common ways of estimating the grout properties, and I won't go through this, but it's in the documentation for cables. It's actually really pretty thorough, and I would highly recommend looking at it if you're trying to estimate grout properties. And then one additional development we put in for cables, which is very common in cables, is pretensioning. And I would if you want to really dig into that, I recommend looking at the manual. Basically, you supply a force, a tensile force, and it will implement that force in each cable as long as it doesn't rupture the cable. And then it will solve for a little bit, and then your model will basically have these cables with some pretensioning in them. Very commonly done in practical applications of cables.